but you've lost the first part, which is the most relevant one, which is quantum processes. So actually the title of the course is Quantum Processes. Okay. Thank you, Andrea. So welcome, everybody. It's quite tough for me to give lectures this time of the morning. I'm still sleeping, so it will take a while to be concentrated. I will try my best. Let me start with a couple of introductions, a sort of general introduction and then a scientific introduction. The general introduction goes as follows. A few weeks ago, I was thinking about how to organize this course, and I thought to distribute a questionnaire to you asking whether you were familiar with some concepts or not. And then I realized that even if just one student had answered, I know nothing about Bloch sphere, in any case, I should have explained what a Bloch sphere is. So I decided for a different strategy. So I will try to be as general as possible. I will try to explain things that for some of you will sound absolutely trivial, and yet I will do it. However, if you at any time realize that you're not understanding, not because of the concepts, but just because you don't know what an acronym means, or you don't know a definition of some formal objects, or things like that, you are obliged, it is compulsory, to interrupt me. It doesn't matter whether you think it's going to interrupt the flow of the reasoning, you have to interrupt me, okay? So that's a deal. And this doesn't mean that you are not allowed to make other questions, so you can make as many questions as you want. And I've also brought my favorite box. This is not the box of the Schrödinger's cat, as Andrea suggested. This is the box, well, it's written in Italian, but it's the box of I didn't understand. So how does it work? You will be given, in a while, a small piece of white paper. During the lecture, whenever you have a question, that for one reason or another you don't ask during the lecture, for instance, because you think it's going to be too long to answer or things like that, you just write it down and then you put the piece of paper back at the end of the lecture. Everyone has to put the piece of paper back in the box at the end of the lecture, even if it's white, because I don't want to waste paper and because I don't want to know who has asked question and who didn't.
What's written on the box?
Okay, sorry. What I did not understand, question mark, what, and so on, okay? And a lot of question mark, okay? So one of the reasons why I like this box, that probably you will stop using immediately after the first lecture, but in any case, it will force you to concentrate up on the question. Sometimes, so you can write whatever, apart from comments on my look and my dresses, apart also from another thing, which is you cannot write, I didn't understand anything. So you have to learn how to formulate a precise question. So if there is some fog in your mind, the box helps you to focus up on what is it that you really did not understand, and write your question in a small piece of paper. And that's very helpful, and I think it will teach you to, ask questions to yourself. Okay? Okay, then another thing I was wondering is what kind of course should I give? Because the topic I will be speaking about is a little bit off track with respect to what you've been learning in the first week. And it stems from a huge literature which has been mostly unknown to most physicists until a decade ago. 10, 15 years ago. It is a literature that was developed since the 70s in the framework of quantum information theory, and only recently has become more used by physicists. Which means that really there are so many things I might have decided to speak about. So I didn't know exactly how to interpret this course. And then I had an idea. I like to sail, and then I thought, okay, this course will be a compass. What does it mean? It means that I will not be able to explain in details all the topics that now and then I will touch. But at the end of these 6 hours, I hope you will have a compass so that if in the future you will find, let's say, CPTP map, And then you go, oh yes, she spoke about it, and you know where to go and look. Okay? So take it this way, which it also means that I will speak about things that I am not an expert about. Okay? So maybe you will ask me a question about details of some topics, and I will not be able to give them to you, because I want you to know that these topics exist, even if I'm not working on them. Okay? So this is more or less the general setting. And a final thing about general introduction. I tend to forget completely about time. So shall we have, Andrea, shall we have a break?
Yeah,
in the
10 minutes break between 1 hour and...
So someone, when you are fed up and tired and you think it's time for a break, just start waving your hand, because I forget about it. I tend to go on until the end, and okay, so you have to remind me. Good. Did you prepare the... Thank you. Okay, so you just let this, and if they are not enough, just ask. Okay, so the title of the course is... I prepared everything thinking about the old blackboard that was in this room. This is where I discussed my thesis, actually, my master thesis. So the new, I don't know exactly how to organize it. You can't have a blackboard where you don't have a central part, you know. You should have either 3 parts or just one, but how can I write here? Okay, let's do like this. So what is a quantum process? Quantum process is the most general and generic term that you can possibly think about. It is something that transforms a quantum state into another quantum state. And this transformation can be due to some physical... Not enough piece of... Didn't you count the students? More are coming. Eh? You go. No, ma fagliele lo stesso, dai. Per favore, grazie. Okay, so the mechanism that causes the change of state can be whatever. It can be a physical dynamical evolution in time. It can be a mathematical transformation. It can be a logical transformation, like those you find when dealing with quantum computation and quantum gates. And because it is so generic, it needs a sort of a different formalism with respect to the one we are used in physics. The formalism where quantum processes live their life is called the quantum operations formalism. And that is going to be the main topic of this first lesson. So quantum processes are studied via quantum operations. There will be a lot of quantum during this course. Overwhelmingly quantum. Okay, so what is the setting? The setting is that of standard quantum mechanics. Standard quantum mechanics in the so-called axiomatic approach. Axiomatic approach means that we will not speak about principles, we will speak about postulates. And in particular, I will refer to what is called the axiomatic approach a la Nielsen. Nielsen is Michael Nielsen, author together with Chuang of this book. which is somehow the Bible for people working in quantum computation and quantum information theory. Okay? And the reason why I choose this approach is because Nielsen reduces the postulates to the minimum number. When you have a look to recent books on quantum mechanics in the axiomatic approach, you find books where you have 5, 6, 7, 9, 10 postulates and even more. And they are all ordered in different ways. So you have to say, okay, a la Nielsen, it means you have 4 postulates that we will briefly go through in the next few minutes. And they have a specific order. Now, I need to write a bit of notation that I will write here. And it will help us understand the setting. So first of all, standard quantum mechanics, it means that to any system you associate a Hilbert space, and this Hilbert space will be assumed separable. What does it mean, separable? It means that it admits orthonormal bases whose cardinality is that of the natural numbers. What does it mean? You can count the element. Okay? So it doesn't matter whether it is infinite dimensional. It must have orthonormal bases such that you can count the elements. It doesn't mean that you can't have continuous bases, okay? But it must admit this kind of countable basis. Elements of this Hilbert space will be indicated by cats. Unitary operator will be indicated like this. Star in This is a terrible way of representing a rho, the Greek letter rho. Okay? I'm not able to make it better. So it resembles a P or something like that, but it's a rho. And I will use it a lot, so get used to that way of writing it.
It's fine.
Pardon? It's fine, thank you. Thank you. I will add a few things at the end that you probably don't know, but we will use them later. These are. And these are. Okay. We will need more, but I will introduce later. So, quantum I will, you're right. POVM stands for positive operator valued measure. It is a very relevant object in quantum information and quantum computation. I will define it later. And yeah, I will define it later. Now, the main tool used in quantum operation formalism is the density operator. So, first part of this lecture would be devoted to introducing density operator. You probably already met a density operator. You probably have called it density matrix. I don't know. Let me say that I will not use, unless it is really necessary or useful, any matrix notation. The reason for this is that when you use a metric notation, you are somehow implicitly assume an arbitrary choice of a basis. because otherwise you wouldn't be able to write the matrix. So to avoid hiding this choice, I will not use matrix notation. Sometimes in quantum computation you use it, particularly when writing quantum gates, simply because you assume the choice being the one of the computational basis. So it's clear that you've chosen a certain basis, computational basis. I will explain what it is. It's trivial. And then you can use the matrix notation. So what is a density operator? As I said, probably you've already encountered it in what is called the ensemble interpretation. The ensemble interpretation works like this. For some reason or another, you know that your system can be in a set of states, say gamma. Well, in a set of, okay, I've not yet explained what a state is, but you understand that, I suppose. And to each of these states, you can associate a probability, which is a statistical probability. So given this set of couples, P gamma and gamma, ket gamma, you build a statistical ensemble. To this statistical ensemble, you associate a density operator, which is written in this way. So this is clearly an operator acting on the Hilbert space of your system. And it has a clear statistical interpretation. I don't want to forget comments at this early stage. Okay, so on the other way, you can introduce density operator from intrinsic characteristics. I hope I spelled it right. And this definition goes as follows. You have the space of bounded operators acting on your Hilbert space that I will indicate with B of H. A density operator is nothing but one of the operator in this space such that the trace of it is equal to 1, and it is positive. Whereby positive, it is meant that the expectation value of rho over any element of the Hilbert space is positive. Exercise. Prove that given this definition, the trace of the squared of rho is less or equal to 1. With equal holding if and only if rho is a projector. And prove that rho is Hermitian. Back in a second. vabbè, never mind. Ok. Now, mi vergogno a chiedere, mi ricordo mai, è minore di 1 o maggiore di 1? Cioè c'era 4. Minore? Perché lì c'ho scritto maggiore. Va bene. Ok. Now, there is an important point here, which is the following. I mean, you tend to think that these two approaches are equivalent, but they are not, essentially because although it's not immediately clear, however, you can have different ensembles giving rise to exactly the same density operator, which means that once you have an operator defined like this, it is not immediately clear what is its ensemble interpretation. The most typical example is the one that you find in a lot of books, is the following. You take a qubit, so meet the qubit is nothing but a quantum system whose Hilbert space has dimension equal to 2. So for instance, you can use as a symbolic orthonormal basis is 0 and 1. Okay, so if you take a qubit and you give this ensemble, sorry. So you have this ensemble, and you say, okay, that means that my system is with probability 1/2 in the state labeled by 0, and with probability 1/4, and with probability 3/4 in the state labeled by 1. Okay. However, if you introduce these other elements, A equal
Sorry, there shouldn't be a comma. So it's a half.
Yeah, I mean, sorry. This one?
Okay.
Sorry. I mean, this is an extended version of this one. So I don't use the curly brackets because it's extended. Okay? So you have A given by this and B given by the same with a minus sign. You can easily check that these are orthonormal. So you can define a different ensemble, which is 1/2 A, 1/2 B. O 1/4, 3/4. Oh, ma lo sbaglio sempre, eh? 1/2 radice 3 su 2. Scusate, ho sbagliato tutto. 1/2 AA più 1/2 BB. Allora, questo probabilità di questo in mezzo. Ok, sorry about it. Okay, sorry. You have to write it this way. And you can, I leave it as an exercise, these are equal. So this property is called the unitary freedom in the ensemble representation of the density operator. Unitary freedom is a concept that we will find at each level of the construction. So we will find unitary freedom for quantum operation, unitary freedom for maps, and it is something that follows from a couple of ideas. One is obviously the structure of the vector space. So if you want from the superposition principle, and you can easily see it here. The reason why these are equal is that you can write 0 in terms of A and B or vice versa with plus and minus. And the other one is that whenever you deal with this density operator, you are more or less assuming that there is something about your overall system that you don't know. And this something, which will be later on an environment or another qubit or something, allows you to have a bit of freedom in representing the objects you are interested in. Okay? Now, the reason why as there is this unitary freedom, it is not always the best choice to use the ensemble representation. Please. The point is that, the point is the environment enters in the fact that the state of your system is described by this object. If there was no environment, you would have a projector, and for a projector, there is not such freedom. A projector, you can only write it in a way. Please.
Maybe what is of essence here is that the state is a mixed state that will remain under any given transformation. Maybe that's also a partial answer to your question. But this will remain mixed regardless. So it doesn't matter the basis. You can never make it pure in a sense.
Yeah. Okay, so you have probably noticed that I've quite carefully avoided using the term pure state or mixed state. Obviously, it is a term, these are terms which are very much used in the literature, especially by physicists. People working in quantum information, they tend to call state a density operator. So in what follows, when I speak about state, I mean a density operator. If the density operator is a projector, meaning that its squared is equal to itself, then you can say that this state is pure. Okay? But in general, a density operator is a state of your system. Let me open a small parenthesis about it. Quantum mechanics, and you strongly see it in quantum information theory, is a theory that despite having been considered, very abstract and theoretical and so on, actually is strongly related with what you can actually extract from measurements. So in quantum mechanics, when you speak about a state, what you mean is the formal object that has all the information necessary in order to reproduce the statistic of your measurement results. Full stop. Which means that whenever you have an object that mathematically allows you to reproduce these statistics, that's a legitimate quantum state. Okay? So in this sense, density operator is not less than pure states or Katz or Brau, things like that. It's just a state. It has all the information you can extract from measurements. Or vice versa, I mean, please.
Well, that's the one side of the coin. I mean, again, the other side of the coin is that we should still distinguish something which is and this is how the environment comes into play. So a pure state can become a mixed state, and I mean, we should not disregard this fact. I mean, like, okay, maybe it's too late, but like from a Lindblad number, of course, you can still go from a pure to a mixed state. So, but in a sense, there's still something happening, like, and that's something has to be captured in terminology. I mean, maybe we are arguing nomenclature, but...
No, but I mean, I agree, and I've also had problem when I started working in this, how to say, field, in renouncing this idea of, as you will see today, I mean, the environment is something that we can and we will explicitly insert in the formalism. What comes out in the quantum operation formalism is, although it is useful in order to understand the physics behind some properties, it is not necessary. So you can also give an axiomatic introduction to the whole story of quantum processes without thinking about an environment. Okay? But we can discuss about it. Okay? Not at this level. Okay, just in a second I will tell you more. So at the moment we are dealing with the first three postulates, and I will briefly go through them with the density operator. To discuss about environment and this kind of stuff, we need the fourth one, and I will speak about the fourth one later. So why am I saying that we are dealing with the first three postulates? Sorry. Well, because you can express the first three postulates in terms of density operator. They go this way. So you have the first one saying that to any quantum system you can associate a separable Hilbert space, and the state of your system is defined by a density operator as I've just introduced it in the axiomatic approach. So from the intrinsic characteristics. So ρ is an operator which is bounded, is positive, and his trace is equal to 1. Second postulates unitary dynamics. You introduce time and you say that if ρ, okay, so in what follows, whenever I will consider time, objects at time equals 0 will have no time dependence. So I will not write ρ0. I will just write ρ. And that is going to be the usual notation. Okay, now we come to the third postulate, which is the measurement postulate, which is the one I want to spend measurement. A few words about, because this is the way quantum measurements are introduced in quantum information theory, which is probably the part which is most different with respect to the usual courses in quantum mechanics. So how does it go? Well, it says that a measurement is an application that goes from a set of results to a set of operators. So these are the results of your measurement of your experiment. To each result, there is a lot of structure. I mean, you have to say it's a sigma algebra, it has some properties, but just think about the possible results of your experiment, okay? So real numbers and open intervals, because they are always open intervals. To each result, you associate an operator, which is labeled by the label of the result. And the properties of these operators are the following.
This is shorthand again for bracket on any cap in the state.
Yes. Whenever I write that a certain operator is larger or smaller than 0, it means the expectation values upon every element of the Hilbert space has that property. Okay. And then the postulate goes like this. Now, let's call these a measurement of the property M. So the probability of finding the result M while making a measurement of the property capital M on a system which is in the state defined by rho, it is this. Now, this is what is called P of M, and these operators are called the elements of the P of M. Now, it's clear why it's called P of M. It is positive operator valued measure. So it is a measure that goes into positive operator. Okay, so this is really to be understood as positive minus operator minus valued measure. No. This is more general.
Okay, but when we write down the sum of M, we always mean in a sense, in an operatorial sense. Right?
Yes, this is, sorry, you're right. Let me write it to be more precise. Okay, sorry about it. I will do this mistake again and again. So when I write that some sum of operators is equal to 1, it means identity. Okay? I know what is your reaction. Why should I go through all these? Well, essentially because this is the most general way of defining a measurement. And as you will see, a measurement is one of the essential quantum operations. And it describes one of the fundamental quantum processes. Please. Oh, no, sorry. Yeah.
Is there some concept of, you have to repeat the experiment a few times, or is there something?
Okay, so repeatability is a crucial point in the construction I will go through, because actually it is only guaranteed for projective measurements, which is actually the last step of the construction. In the case of P of M, there's no no connection with repeatability, essentially because no one tells you what is the state after the measurement has been performed. And that's a key point in P of M. So the main difference between P of M and the other two types of measurements, general measurements and projective measurements that I will in a second introduce, is exactly that this kind of definition doesn't tell you anything about what will happen after the measurement. Meaning that if you want to actually reproduce this probability, you need to be able to prepare again and again your system in the same initial state rho. Okay? Which is very crucial when you run algorithms, as Laura knows, because if you want actually to measure the output, and the output is not perfectly defined, meaning that it has a probability distribution, you actually have to run the algorithm many, many times in order to gain enough statistics to reconstruct that probability.
Like M are possible values of
Yes.
experiment.
Yeah.
So we
If you want to build this, yes. Okay. Or you may have, as you all know, I mean, you may have a lot of systems which are exactly identical, and you perform the same measurement of all of them. Okay. Notice that in this construction, there's no relation with this M and what you usually call the eigenvector of some operator. Okay? And the reason being that most of the time these M are not actually eigenvalues of anything. They are just click, no click, beep, no beep, red, black, blue, white. Okay? So it's really the output of your experiment. And there's no connection with the eigenvalue of some operator. Now, a little bit more you can say going to, so if this is third postulate, sorry. One. Then you have third postulate bis. Now, if you can define, you can extract these two operators such that this equality holds, then you can deal with what is called the general measurement. The difference is with the general measurement, you can actually define the state of your system after the measurement, given the result is M. Okay, so this notation means something given something else. So the state of your system after the measurement, so the output, given that the result of the measurement was M. Okay, you can define this using these measurement operators. Okay. And okay, let me write it properly. So this is, and this is exactly this object here. These operators M are called measurement operator. So it is not completely rigorous, but if you are able to repeat your experiment many times, or if you have a lot of systems all prepared in the same state row and you can perform the measurement on all the systems, you can, in a sense, define a general state after the measurement in this way. Well, the way to construct it is clearly you have the probability of having this result times the state given that result, and this is nothing but So this is the first time you see clearly a quantum process and why a measurement is a quantum process. Because you start with a state and you get with the final one, which is different from the one you had at the beginning. Remember this structure because this is actually the structure of a quantum operation. Please.
Sorry, can you discuss later the second line? So what is P out given M? So
is rho out. Sorry, it's not. Is rho. Sorry. Yes. Okay. Is the state of your system. So you have your system. You make a measurement. You read the result is M. That is the state of your system. Okay? Everything may look more familiar if you make the last simplification and you take that these operators are, guess it, projectors. Okay? So if these operators are projectors, you are back, you land in your familiar situation, which is the one you've probably already met. So let me write the P3 ter, which is when these operators can be written as projectors, whatever this labeling may mean. Okay? These labels simply mean that you have a one-to-one relation between results and states, and if you start from this, you can build all the theory that you find in normal textbook in quantum mechanics about measurement, and this defines what is called PVM, or projective measurements.
So this there means that EM are also projectors then?
Sorry?
M are projectors, then EM are projectors as well?
Yes, yes, of course, yeah. It's just a bunch of projectors. In all the expressions you get a lot of projectors that obviously simplify.
Could I ask you conceptually what
yes,
the reason of separating EM to this restriction? So if M is a projector, there's no reason actually of writing like that. Could you give a more general intuition on why we want to separate EM and write it as this form? So in essence, I'm asking what is the difference between M, capital M, and EM?
Okay, so the reason most of the time you actually have no access to these operators here. Because you only have the result, you have the state, and most of the time you can only have access to this construction here. And you are not actually able, from the physical viewpoint, to understand what these operators are. Sorry. Because you see, you get this one, and it is not trivial, formally, to express these operators and to understand what they are from the physical viewpoint of your experiment.
So I hit the operators.
Yes. Yeah. Please.
Is P3 is just a particular case, like if you write EM as
Yeah. Yes. Yeah.
So we haven't seen like when
No, and it really depends. As I said, this is a compass. So, for instance, if you go through the literature, you most of the time will find P of M. And you, what's P of M? P of M. Sometimes they speak about general measurement, and they speak about measurement operators, and they speak about the state of your system after the measurement. Okay, that's here. Okay. Then sometimes they speak, very rarely I must say, I mean in quantum information it's very rare to speak about projective measurement. However, if they speak about projective measurement, it means that you are here. Okay? So there's no specific reason why one should choose one approach or the other. It really depends on what you are doing, on what kind of process you are studying, and what kind of experimental setting you are considering, and so on. Okay. Wanted to say something else?
No question.
Please.
In the case in which M began is a projector, then throughout conditions to M is just a projector itself.
It's, I mean, this is just a collapse.
Yeah, so out becomes a projector.
Yeah.
Okay.
It's just, the collapse rule. Okay. By the way, this is also called the minimal interpretation of quantum mechanics. So when you do not specify what is the output of your state and you only give the probability distribution, you get this minimal interpretation. Please.
So if you start from a pure state, that is on what code, but that's
Okay, a projector.
then after the measurement is not a pure state. Could be a pure state again or not, right?
Okay, so if
I
you...
have a pure state and then the measurement is projected, it remains a pure state.
Yes,
That's a standard test.
yes.
If I do another measurement, the output is not a pure state. Need
No.
not be a pure state. I'm understanding right.
Okay, so if these objects here are projectors, it will be a projector.
Yes, yes.
So a pure state. If they are not, it's not going to be. Okay. So essentially, these two approaches here allow you to insert into the probability distribution that part of the probability that is not intrinsic to quantum mechanics, but comes from the very structure of the state. Okay? Sure. Please. Pardon? M can be whatever is, the number of M you have is just related to your experiment. It must be less than the dimension of your Hilbert space if the dimension of the Hilbert space is finite, but it doesn't need to be as large as. Okay? That is only the case, you have as many M as the dimension of your Hilbert space only when you have orthogonal projective measurements. So where, your measurement operator are one-dimensional projectors. If not, you can also have, for say, a quantum harmonic oscillator, you can have just 2M. It depends on your experiment. Okay. There is a very important theorem which is called, where shall I write it? Here. Sorry. Naimark dilation theorem. This spelling depends on books. The Naimark dilation theorem is the first theorem you encounter where you play this game of the environment. What it says that any P of M is a PVM, is a projective measurement upon an enlarged Hilbert space, which should be clear at this level. Okay? And this is very relevant when you try to give dynamical models of measurements. Because what I'm not saying at the moment is that when you want to describe this kind of processes dynamically, you really need to design the interaction between your measurement apparatus and your system, which means to go into the details of this structure. And you can do it for projective measurement. There are several models that work. But at the moment, there's no model for P of M. And the only way you can dynamically describe a P of M is using the Naimark dilation theorem. So you have your system, and then you add what is called an ancilla. So you enlarge the Hilbert space. Usually, you at least double it. Okay, so you put it together with another system, which is an ancilla, and then you perform a projective measurement of a local property just on the whole system. Again, just write it down. Naimark Theorem is essential in quantum information theorem. This is the name. You find it in books, and it has many useful applications. Please. The statement is that any PVM, any POVM, so any of this process, can be transformed into a PVM, projective measurement, upon an enlarged Hilbert space, meaning upon a system whose associated Hilbert space is larger than that of the original system, the one upon which you define the POVM.
So that then the projection is local.
Yes. Yeah.
It's a theorem, not a postulate.
It's a theorem, and it is demonstrated.
Okay.
Now, at this point, we have everything to start with the fourth postulate, to speak about the fourth postulate. Madonna, ce la farò la bisogna, questa lavagna. So the fourth postulate is the one introducing subsystems. So if you want... È l'ora di fare la pausa? Okay, let me just tell you about the fourth. Do you want... shall we make the... Okay. Well, it's very simple. So the fourth, it simply tells you that if you have two systems, one with Hilbert space A and the other one with Hilbert space B, and you want to have the Hilbert space of the composite of the system that you obtain just putting them together, this is the way you construct it. Okay? And as you probably all know, this is the postulate where entanglement comes into play. And okay.
So with the Naimark relation, this is actually the ancilla playing the role of something that enlarges the Hilbert space.
For instance,
Okay,
yeah.
so
Yeah, exactly. Now, from this postulate, actually, it follows a sort of modification postulate saying that the state of one of the two subsystems is equal to the trace over the other subsystem of the global state. So what did I write here? Rho is the state of the system A plus B. Then the state of the subsystem A is defined like this, and this is the partial trace. We will start from here in the second part of the lesson. So, please.
So is this now a definition, or is it a postulate, or is it, or does it follow the other?
Very nice. There is a very nice box in Nielsen's book. You know that this book has boxes. Boxes are sort of parts where he explains in detail things. And there is one which is titled, Why the Partial Trace? It's very nice. The reason for this is essentially a definition. And it is a consistent definition in this sense. If you define the density operator of a subsystem in this way, you easily verify that you have all the ingredients needed to reproduce the distribution of measurement results, which is always your guideline. So the key point is you must be able to reproduce the probability distribution of experimental results. If you have all the information necessary to do this game, that is a proper state. That is a legitimate state. So in that box is nicely shown that if you define the state of a subsystem in this way, and then you perform measurement locally on the state, on this system, this object here gives you all the information needed to reproduce the probability distribution of the measurement results. So it's a legitimate state. Okay? See you in 10 minutes? Okay, thank you. We can close somehow the logical circle of the first part of the lecture, of the lesson, simply by saying, and I leave you as an exercise, I tell you that you need to know what a Schmidt decomposition is. If you don't know, just ask me later, and because otherwise you can't solve the exercise. So the point is that you can demonstrate that any reduced density operator, meaning defined in this way, is a density operator, and vice versa. Okay? So when a density operator is defined like this, is usually called reduced density operator. So you have three ways of defining density operator. One is via statistical ensemble. The other one is via some intrinsic characteristics, simply saying is a positive operator with trace equal to 1. And the third one is via this definition here. The three definitions are completely equivalent, the only drawback being that the first one has this unitary freedom I spoke about. So the same ensemble different ensemble can give rise to the same density operator. And clearly enough, here you see where the density operator actually comes from. As I said before, there is always, although sometimes you simply don't want to think about it, there is always this idea of something else, an environment, an ancilla, another system that is around. And you don't want to have information about it, and yet you have to consider it because it is interacting with your system. Or it can also not be interacting, but it's entangled with your system. So you always have this, the reason why we use density operator essentially is that most of the time we cannot forget about the fact that there is this other system. And obviously the situation where you see it more clearly is when this other system is what you call environment, so all the rest. But as I said, it's not the only situation where you have this problem. When you deal with 2 qubits and you think about a C-NOT gate, a control NOT gate, 1 qubit is the environment for the other, even if they are exactly the same. And the existence of entanglement between the two is the reason why one of the 2 qubits cannot be described by a projector and need a density operator. Is this clear? Okay. Now, there is a very interesting problem in many-body physics related with the definition of a density operator. I'm not an expert on it, so this is one of the topics I will speak about where I can't tell you much. But I think it is a very interesting problem. It is called the quantum marginal problem. Perhaps you already know it. How does it go? It goes essentially asking the reverse question. So if I have many subsystems, and I have the density operator for each subsystem, how can I check whether these density operators are consistent, meaning that they all derive via partial trace from a global state, okay, or not? So I will briefly explain what the quantum marginal problem is. So suppose you have n subsystems. And you divide them into a certain number of subsets. Let's say the notation is too complicated, but never mind. Okay, and then you start playing this game. Whatever, okay? And for instance, you say that this is S21, S22, uno, ce n'è uno con 3? Sì, questo 1, 2, 3, questo è S31, S23, S24, sì. So suppose you know the state of each subset. The quantum marginal problem give an answer to this question. Does it exist a state for the global system? Let me indicate it like this, such that each reduced density operator is compatible with it. Is it clear? Okay. Now, this problem is very relevant, for instance, in one-dimensional spin chains in order to find the ground state, or in general to solve many-body systems. And just let me show you why.
The answer is yes or no?
It depends. It is a problem. Okay?
Put a question mark on the equal. Or on the exist. Okay. Okay.
You're right. Sorry. No, you're right. Because I say it in words, but then I don't write it. So the typical situation where you find this problem is when you have to find the ground state of a many-body system. Think, for instance, of a spin chain with next neighbor interaction. So this is the division of, and so on. And then you have a Hamiltonian, which is the sum over I of nearest neighbor interaction. And you have to find the ground state, well, actually the energy of the ground state, which is the minimum over all possible rho of the total state of this object here. Now, this is an optimization problem on a Hilbert space that grows exponentially with the number of elements of your spin chain. Is it called an NP-hard problem computationally, this minimization? Okay, so it's a very difficult problem. But if you can solve the quantum marginal problem. So it means that you have available the reduced density operator, which are compatible with this. This same object, you can write it like the minimum over all compatible, where compatible mean what was written here before, okay? So all compatible rho 2. Rho 2 tilde means they are compatible and they are reduced density operator for two spins, two neighboring spins. Okay. Now, do you understand the point? I mean, here minimization is not just over all possible density operator here, but it is just over all the possible two sites density operator which are compatible.
What is compatibility?
Compatibility means that they all are obtained as partial trace of all the rest over an original density operator.
Okay, would you write it down?
Oh, yes, sorry. I thought I had written, but again, I say things and I don't write them. So what does it mean compatible? It means, so let's say rho I, k, rho k, j are compatible. Actually, you can also change the number of elements, k prime, say. If, and only if, rho k I equal trace over n minus s k I rho. This is I'm referring to the previous picture, okay? This equal is essential. So they are the partial trace, the proper partial trace of the same global state. This is what being compatible means.
And what can rho 2 then in this case?
This is rho 2I. So this is the density operator, dimension 2, site I. So, for instance, if this is site I, is the density operator for this couple here.
Couple 12.
Yes. 2, you see, K is the index, the lower index tells you how many elements are in your subset. Is your subset.
Physical element.
Yes, physical element. And I number the subset. Okay? Please.
I don't understand what are the elements. I mean, if I have a system described by a Hilbert space, what are the elements? I mean, for me, a subsystem is a subspace, essentially.
Okay, so all this part here arises from the fourth postulate. Fourth postulate tells you that system and subsystems are not related by the Hilbert space of one of the subsystem being a subspace of the original one.
Okay.
Okay? That is not the case. It's very relevant. So when you speak about subsystems, you speak about something whose Hilbert space is tensored. Is exactly. Okay? Please.
Why we are interested in particularly calculating the zero with the two-body density matrices? Because it's just simpler, or
It's just an example.
okay.
No. I mean, the quantum marginal is a problem that can be formulated in all possible different ways. The way I formulated before with K and I is completely general. For instance, it is a problem which is very relevant also in optimization problems with networks, with neural networks or this kind of stuff, where you really have, subsets which are in a higher space, not just along one dimension. The reason why I mentioned this one is that on this problem here, there are a lot of papers. So if you look on Google, quantum marginals, one-dimensional spin chain, you find a lot of very nice papers, and you find all these geometrical constructions with polytopes and all this stuff, which are, I think, interesting. So it may happen that you will find them. Okay? And the key point is that, sorry, I don't know if I said it, but this problem here is not NP hard to be solved. The complexity of this problem from the algorithmic viewpoint grows polynomially with n. And so it's much simpler. So if you are able to reduce the set upon which you want to minimize this object to those which are compatible in the sense that I've just said, that problem is much simpler to be solved. This is just to give you an idea about a possible use of density operator in many-body physics, which is, sorry.
Is rho 2I associated with the pairs, or should it be something over the rho 2I for every of these pairs? Because I'm a bit confused how to produce
Yes.
the formula,
There's sum over E, sum over I.
But the Hamiltonian has the sum over I anyway. Does the sum come from the Hamiltonian or comes from a different rows sort of associated to every side?
It's the same. It's the same because these only acts on the one having the same I, and then all the rest disappears. Because so this is a trace just over the two sides, obviously. When I don't write anything, it means it's a complete trace over whatever is the argument of the trace.
Okay, that's clear. But I was thinking you need two only because you have nearest neighbor.
Yes. Yeah. As I said, I mean, if you have different geometries, the whole setting changes, but the idea is the same. Please.
So, is it really a matter of existence of such metrics or a matter of finding?
No, of existence, because consider that you have, okay, so it depends on where you start. Suppose you have the density operator for all the subsets. There is really no reason why they should all derive as partial traces of the same global state. There's no theorem guaranteeing that. The other way around is obvious.
And then the system is described by a state anyway, so...
Yeah, the point is that this will lead you back to Z. Of course you can solve this, no problem. But this is difficult, and this is easier.
So you know it's because you basically just the diagonal block, small blocks around the diagonal.
It's more complex. As I said, I'm not an expert on quantum marginals, but when you see the structure of the problem, it really gives you, essentially, you reduce, in a geometrical description of these operators, you reduce the number from the volume of a polytope to just the surfaces. So, but as I said, I mean, you have to look at it carefully. So at the moment, you simply, must trust me that it's simpler. Okay? Okay, that was an example. Block sphere I will not speak about now. Okay, let's go on. we have to move towards quantum operations. While I clean the blackboard, do ask questions if you have some. Okay. So quantum operations, as I said at the beginning, quantum operations is a term that indicates the formalism used in order to study quantum processes. And again, there are three different ways of introducing quantum operation. One is called the system plus environment approach, and you can guess why. The second one is called the operator sum representation approach, and the third one is the axiomatic approach. Today, we will deal with the first and the third one. And tomorrow, we will deal with the second one. And the three approaches are, as you can guess, increasingly abstract when you move from the first to the third. So the system plus environment approach is the one that has more direct contact with physics. The operator sum representation approach, it is somehow in between. And the third one, the axiomatic approach, is the more abstract one. They all have their pros and cons. And as we are physicists, I will start with the first one, because I want you to finally see the environment appearing. So we have two systems now. Okay, so this is, the system plus environment approach to quantum operation. You have two systems. Your principal system that will be hereafter called gamma, and something else that in this approach, as you can guess, is called environment. I will indicate environment with a capital Xi. So this is capital Xi. Okay? The total system is just the sum of the two. Now, sometimes you can write, if you don't like plus, you write united, do what you want. I mean, key point, you have two systems, principal system and environment. Okay. Now, you assume that this global system is isolated. It's a trivial assumption in that if it is not, you simply enlarge your environment up to the point when you include everything which is interacting with the environment itself. Okay? So if it's isolated, then I can use the second postulate and write that if my system, global system, when I don't write any index, I mean the global system, is in an initial state rho, at a later time t, it will be in a state described by a unitary with a parametric dependence on a continuous object, which is time. Now, in this approach, time is a continuous parameter. In the other approaches, there's no time whatsoever, as we will see, which is one of the reasons why the other approaches are useful. Now, what is a quantum operation? Sorry, what is a quantum process? is something that send input output. So in general, when I have to study a quantum process, I don't speak about initial time and final time, but better to speak about input and output. And it is important to realize that these states need not be states of the same system. So as we will see tomorrow, you can easily study a process that connects the input state of a system A with the output state of a system B. Very typical situation. In the system plus environment approach, this possibility is ruled out. What you actually concentrate upon is how gamma, the state of your principal system, is transformed due to the interaction with the environment. Okay, so in general, you don't have the same index here. In the system plus environment approach you have. So the point now is, okay, I have this, and I want to write this. No problem, I know, because of the evolution, let's say, of the fourth postulate into a sort of extension of the first, that this is nothing but the trace over the environment of the global state. Now we have to work with this. Now, what is a quantum operation then? It is not an operator. As we will see, is actually a super operator. So it is something that acts on operators. But it is something that I want to be able to write in this way. Some is usually indicated by this calligraphic E, map. So I want to have a quantum operation applied to a state, in this case will be gamma, that gives me, as a result, this one. Now, it seems trivial, but it is not, because this operation here must not depend on its argument. Okay? If I want it to be applied to rho gamma, it cannot depend on rho gamma itself, because otherwise it's not an operation. So, let me write, and that is not trivial. Actually, it's not true. In general, we can't do it. So, let me now let me now write the global state of gamma plus psi as a separable part plus what's left, where this is the partial trace and this is the partial trace. Okay? I can always do it. Because I simply, I have my global state. I determine the two reduced density operator, the two states. What is left, I call it delta. Notice that this delta is not a state. It's very easy to check that the trace of this object is not equal to 1. So it is actually equal to 0. So it cannot be a state. Okay? Now, please. Why I introduced it? Because I need it. I mean, there's no reason why. That is a sort of I can always write rho like that. If you want, once you have defined this, you can simply say that delta is rho minus okay, it's just a trivial definition. Now, what it represents, you will see it later. It actually represents the part that, okay, I slightly anticipate, but never mind. It represents the part of the state that does not allow you to make a Markovian approximation. It represents the part which is entangled between gamma and psi. So if delta is equal to 0, what it means is that gamma and psi are separable. Okay? So this is the definition of separability with density operators. Doesn't matter whether they are projectors or not. That is not relevant. Okay? Please.
Your definition, because of the cyclic moment of the trace, I could get rid of the operator, right? So
No, because this is partial trace.
but the cyclic moment still applies.
No. If the operator X, not Hilbert space, the cyclic doesn't apply. Never. You can easily check it. Okay, that's crucial. I mean, remember this because we will use it a lot of times. I mean, whenever you deal with partial trace, the properties that hold for complete trace do not hold anymore. Okay? Okay, let's say by subtraction, okay? This is separable. Oh, sorry. It's not a state, yes.
So, because which mathematical properties?
The trace is equal to 0. If you evaluate, trace of this is 1, then you evaluate the trace of this considering that each has trace upon its Hilbert space equal to 1. And essentially you have 1 equal 1, so the trace of this is 0, so it cannot be a state. Okay, so boom. Now I can write that trace this way. Let me concentrate up on this term here. Allora, we know that this operator can be diagonalized. It's a Hermitian operator. So let us choose some spectral decomposition of this operator here. Psi, pi, psi, psi, psi. Sorry for all this. These are small psi. Okay. Now, once I've chosen a spectral decomposition for this density operator, I will perform the partial trace using the same basis. So I get sum over psi and psi prime of okay, let me write it like this. notation is slightly sloppy, but you can survive. Let's do it like this. Now, you define this operator here. Notation is not the best. Mathematicians always get very angry when you write things like that. This is an operator acting on gamma. Okay? You shouldn't write it with Brian Katz with an operator inside. But you understand what it means. Are you happy with this? Can I use this notation? Okay. So this is an operator acting on both gamma and psi, on the composite system. And what is left after you've done this inner product just on the Hilbert space of psi is an operator acting on gamma. So this is an operator acting on gamma. Are you happy? Okay.
So you have inserted the identity as well, right?
Pardon?
You have inserted the resolution of the identity along the way as well.
No, actually, I've just inserted this here.
Because you have two signs, and the identity, because you have a double sum.
No, it's just one sum is from for the trace. The trace over psi is sum over psi prime. Yeah. So the trace is gamma over psi prime, and the spectral decomposition is sum over psi.
Okay, so is it orthogonal set size?
Yeah. If this is not complete, you can complete it, just assuming that some p are equal to 0. Okay? So you can really consider it as an orthonormal basis. So this is an operator acting on the Hilbert space of gamma. When I say acting on gamma, I mean on the Hilbert space of gamma. Now, with this definition, you can forget about this term here by now. You can write the evolved state of your principal system in this form. Sum over psi and psi prime, b psi prime rho d dagger. Yeah.
Is the psi prime
This one, no.
So what is the reference to psi prime? Why does it only depend on the psi?
Psi prime here, psi here.
Okay, sure. How do you make sense of the fact that it doesn't depend on the psi prime and only the psi?
Because by definition, it's just a definition, is how it comes. Okay. You have to insert the square root here, because otherwise it doesn't work. That's it. So remember, one of these comes from partial trace. Partial trace is not weighted by anything. It's just the sum over all the diagonal terms. You have one here, one there. In the middle, you have this object. These are probabilities, so you can define the square root, because they are positive. So it's just a definition. Please.
Sorry, I did not understand what happens with this term today.
It's just there. It's just waiting for me to consider it. It's still there. Yeah. Okay? Are you happy with this or not? If you want to get, to understand all the everything, you just write these, you decompose these into Brian Katz acting on h of gamma and h of psi, and you do all your calculations and everything works. Okay. Key point is that, this is relevant. You really have only one p of psi upon which to play, not two. Okay? This is just definition. So here, as our friend suggested, we still have this. Oh. Okay. Let's concentrate upon this. These we like. Well, we could add a dependence on T. We could also add a relevant dependence on rho of psi. So if I have to write this explicitly, this is an operator that depends on time and on the initial state of the environment via this decomposition and these probabilities. But it does not depend on the initial state of gamma. So it's okay. So we can use this to define a quantum operation. This is something that I can apply to a state and obtain a new state. Please.
If we are the Markovian approximation, it's only this term we care about and not the other one. If there is limited formally.
Yeah. I will also explain why now.
Okay.
So, as I said, okay, so this is the first quantum operation that you have explicitly derived. You immediately see that unitary evolution are quantum operations, obviously, because if you have unitaries here, it has the same structure. And also measurements, general measurements, not P of M, but general measurements are quantum operations. They have the same structure. Now, we have to consider that delta time term. Now, unfortunately, we cannot deal with this in any way. There's no way you can have fun and try to do it, to write this object here as something applied that does not depend on rho of gamma, applied to rho of gamma. Okay, so this is never going to be a quantum operation. This is never going to be something that you do to a state that does not depend on the state itself. So as far as this term exists, you cannot define the evolution of your principal system via a quantum operation, which obliges us to consider only the situation when, I don't know what to, oh, sorry. The initial state is separable. So, if the initial state is separable, which means that delta is equal to 0, then I can play this game. I have my initial state. I let it evolve via a unitary global evolution, and I move it into something which is the total state of the system at time t. And then I can either trace here and or trace here And if I have this condition fulfilled, these two objects are related by what is called a dynamical map or quantum operation, which is defined up there. And whether you want to go this or you go that, you have the same result. Okay. Now, when this scheme works, which means that delta is equal to 0, these are called, depending on the community, CPTP map. And I will explain what this acronym means in a second, or UDM. So UDM means Universal Dynamical Map. This is the term used by the community working with non-Markovianity, studying Markovian processes and this kind of stuff. CPTP map means completely positive trace preserving maps. And this is the term used by the community working in quantum information theory. They are the same thing. There is a theorem. It's not easy. I will either, what time is, I have to stop, I guess. No? Yes. Okay. So tomorrow I will explain better what a CPTP map is. However, there is a theorem demonstrating the equivalence of these two. Completely positive trace preserving. Like POVM and CPTP are the most used acronyms in quantum information theory. You find them everywhere, so you have to get used to them. Just let me finish with one thing which is relevant, and I don't want to leave it to tomorrow. So what if there is this term here? No, sorry. No. I want to say another thing. So take the best situation possible. Delta is equal to 0. Then you have your map bringing you to T. Suppose you want to stop before, at an earlier time, say T1. Well, you can easily check that this is still okay. There will be another parameter in the map, but it's the same map, and it's still a UDM. But there's no way you can go from here to there. Simply because the interaction, if it's not trivial, will build entanglement. Will for sure transform the state of the global system, so that here there's no way you are going to have a state of this form. There's really, apart if you are considering a non-interacting unitary. So this unitary represents an interaction between the two systems, and this interaction, unless it's trivial, will build entanglement, will move or discord, some sort of correlations. So will not, unless for very specific situation, transform your state go from a separable state to another separable state, which means that you can go here, and then you can't go with the same map into later time, which means that you cannot define derivative with respect to time. I leave you as an exercise. Think about it, and we can discuss tomorrow. So you can't have differential equation for solving this problem. That is the key point of non-Markovianity. Non-Markovianity means there's no master equation. There's no way you can write a derivative with respect to time. And the reason being that the way, when you write a derivative, you have a function at a certain value x plus epsilon minus f of x. But if f of x plus epsilon doesn't exist, you can't have a derivative. Please.
You can cover memory kernel topic. You could still have.
Yeah.
You're saying that we cannot define local operations in time.
Yeah.
That's why we don't have derivative.
Yeah.
But we could get away with an obvious.
Yeah, I mean, you can have an integral differential equation. When I say differential equation, I mean not integral differential. You can have an integral differential equation that still means that you are non-Markovian. So key point, you are not Markovian, which means no differential, purely local differential equation. You can have, obviously, integral differential equation, where you have a memory kernel, for those of you who are familiar with this. I will speak a little bit about this tomorrow. And yet, you have to, each time, verify that the memory kernel is, as they say, legitimate, which means that it actually is consistent with this kind of derivation. I will better explain tomorrow. Okay, sorry. Yeah, I'm sorry. I went long. Thank you. See you tomorrow.